I'll be showing some tricks and things to do with the MATLAB. Let me just first click on the correct kind of things. So how many of you have actually used MATLAB before? Good, excellent. So start your MATLAB. Just check that if my streaming is okay. Yes, streaming is just fine. Maybe I'll just move this a little bit smaller there. Wait a minute, the streaming is not fine. Now it's more fine. Strange. So now we are ready to go streaming. Good. So that's the classical view of MATLAB. So basically what we have here at the middle, there's a command window. And yes, MATLAB is a command driven like kind of environment. If you are used to use the editor and do the scripts there, it's just fine by me. However, I will be mostly using just a command line. And then after I have done, there's also command history. So it shows every single command what I make here, also the mistakes. I will publish the command history after the show, so you can take a closer look at yourself what I did, including the errors and mistakes. Okay, on the left hand side there's the current folder view. You might actually want to go and create a directory, subdirectory for each exercise what you are making. So everything is under the document, under the folder documents MATLAB, and current folder. I think you can make a subfolder here, call it exercise 1, and go there. So basically just keep track on your stuff. Okay. At the moment there's on the lower left corner there's a workspace, but it's empty since I haven't created any values. But anyways, if I create something like, wait a minute, we had some basic functions. Yes, I could, for example, create a nice set of zeros and then 1 and then 0, 0. So what I'm going to do is something like this. So we have a index vector space, that's the value, just to show that where 0 is. So I just want to make 1, 2, 3, 4, 5. So that's the indexes, and then the values like that. So that would be unit impulse function sampled on that region of interest. Okay, so how to do that one in MATLAB? We need basically both the n and then these values, but we can always just tabulate the values. I will just start with the same, that was the delta function as a vector. So I have 0, 0, 1, and then 0, 0, 0, 0, 0. So yes, so 2 zeros, then 1, then 5 zeros. Okay, and it looks like that. Then I can do the indexing. So I can do the same thing for indexes, but this would be kind of stupid way of doing, or not stupid. There's no wrong way. There's no stupid way. There are just some ways that saves energy. For example, you can use the auto indexing. So -2 to 5. Okay. So that's actually, if you have just a colon operation, then this is from 2. And with step size 1. If you do not define the third parameter there, then it's basically just from -2 to 5. And here on the workspace browser, actually you can take a closer look if you want to, but I don't know if that gives any more information. But anyways, it's a tabular view of the same thing. Okay. Now these I can plot them, right? You can use the plot, but it looks funny with the discrete time samples. You would like to stem plot it. Stem, and then okay, wait for a while. It gives you some information there. So stem xy, meaning the horizontal axis first, and then the values. So horizontal axis n, the values like that. And there we go. I will dock it there so it shows up also on the stream. Okay, so yes, it looks better than what I showed on the whiteboard, but on the other hand it also looks worse. I really hate when these numbers are touching the axis. So you might want to expand the view a little bit so to show the data, since if you have crossing lines, too many crossing lines, you start making mistakes when you're interpreting the data. So show all the data, but not at the top of the axis, unless it's totally, if it must be there, then of course you leave it there. But one way to actually fiddle with the axis would be on this figure menu. All right, let me try my luck here. All right, so you can start using this kind of tool. On the other hand, my favorite, okay, let's see, let's put it back to this one. My favorite is using the command lines and just give command axis. Okay, and you give the limits. X limit -2.5. Remember what I told you about the decimal point. And then for 5.5, that takes care of the negative side, and then maybe the x-axis, and then the vertical axis from -0.1 to 1.1. All right. So that's how you scale the axis, so the data doesn't hit the axis anymore, except the x-axis, because those points were on the x-axis, but it's already looking better. And of course you need also, if you have a figure and you are doing documents, you want to also label it. X label, Y label, title. X label and then Y label. That was title. That is Y label. This is simply value, and X label would be index. Something like that. Okay, that's better. And now for documenting purpose, you can start making this document proof, and that's what you get by saving the plot as, let's see, where does it go? Print, save as, okay, there. Save as something that can be published. Okay, so when you are start doing the exercises, you will first start it by opening a template. which will be a web document at the end. So you want to use a web approved document type. So basically JPEG is fine, PNG, PGM are fine, PPN is fine. The other ones I wouldn't trust too much. I think JPEG, GIF and the portable network anything are web proof, the other ones are not. They are platform dependent. Especially Windows, anything which works with Windows usually doesn't work with all browsers available. I wouldn't trust that one either for web documents. So simple. I think that JPEG and GIF would be the best ones. This one doesn't have GIF. Why? It's licensed property. You have to pay if you generate GIFs. Okay, so maybe JPEG. Or actually my favorites are the portable network graphics file, because it's bitmap file and it doesn't have any artifacts. So it's basically what you see is what you get, more or less. Okay, just not that one. PNG. I'll just call it a test1.png. And as you can see, it did something for the picture. I will just want to take a closer look. What does it look like? Exercise 1. Oh, that's nice. Very good idea to check what it actually looks like before submitting it. Okay, good. So that's fine. I have some answers there too. I'll show you how to work with the template. So on the home page, exercise 1, there's a template. When you open it, make a working copy of this one when you open it, which means you need to be logged into Google. Log into Google account and then make a basically here, very easy, make a copy, and then after making a copy you can work with it. So you can start editing it, since now it's yours. Move it in some meaningful directory, or I don't care. As long as you can share the link. Share. See, advanced properties. Anyone with the link can comment. This is how I would like you to share all of your the returns, reports. This way there's a method for me to give feedback on every single mistake you make. Or if you don't make a mistake, sometimes I just put a comment, nice work, just to show that I actually read your document. Okay, so pay attention now. So this is the easiest way of losing 1 point. Don't share it properly. Immediately 1 point goes like that. Done. If I cannot open it first, 1 point goes away, never comes back. Then next time you share it wrong way, another point goes. Okay, so just technicalities. This is just technicalities. You really have to return it so that anyone with the link can comment. Okay, but anyways, save. Oh yes, that's a nice address, but I will use it later on. Okay, now you are ready to start working with the exercise. I'll just show you some MATLAB things, but anyways, the group number. Don't worry about the group number. Actually, the most important is that let's see, maximum 3 students in one group. work in pairs, since that's the most efficient way of working on this kind of exercises. Pairing up is a smart thing to do. Read the instructions. Basically, I go through the instructions right now, so share it properly. Okay. And otherwise, this is quite self-explanatory. There are some questions, generally 10 questions. Each of the questions are 1 point, and then you basically start answering, like create an index vector from -4 to 14. Wow! Hey, wait a minute, I did something here already. Maybe that would be the right kind of comments on that one. So copy. Have you ever heard of copy paste? That will be just good answer. So they are the commands that you needed to in order to create the index vector of, but of course here this is different scale and that kind of thing. If I want a picture, then, well, this is no magic. Just insert image. Choose file to upload. Whoa, this is somewhere. So documents, MATLAB, exercise 1, test1.png. Yes, nice picture. Maybe a little bit small, so basically you might actually want to do some rescaling of stuff to just to make it say well, I can still read it. Sometimes I get so messy pictures that I have to just, you know, send it back, do it over, so that I can actually see what is happening there, but not too often. Okay, usually that's the way. In some cases, actually, I do have some links I want. For example, here, save the sound sample. But I will show you that one later on. Okay, and okay, back to this one. Just remember that I have a kind of, let me show that again. So what did we do? Just to make sure that everyone was awake. So basically, get the template of the exercise, make it your own copy, share it so that anyone with the link can comment. Done. Then start writing your names here. Okay, don't forget to write your names, since I always have nobody, some people called nobody to pass the course, and I have no idea how to mark it on the student records. Okay, so yeah, and copy paste the commands from MATLAB. If there is a graph, insert the graph what you made. That's why I want those graphs as the some network approved format. Okay. And now back to MATLAB window. Good. Okay, so we got our first commands, and then actually you can also generate this delta using the index function and using the definition of delta. So let's see, delta the other way. So delta n equals 1 when n equals 0 or 0 otherwise. That's the definition. And we could actually just used first generated the region of interest and then just say dd equals to nn equal to no test if n is equal to 0 and okay, so this would give us true false kind of array. We do casting to double. So testing if n is 0 and casting to double format. Okay, so all the calculations in MATLAB actually are done in double precision. There are some limited number of things you can do on integer arithmetic, but double is the native data type in MATLAB. Okay, so that does the same thing. As you can see, nothing changed on the DD. And you still can stem it and put the axis correct there. No magic. Okay, then an example. How about if we want that the heavy side at n-1? So this is actually delayed delta. Oops, a delta. Delayed delta. So delay by 1 time step. So basically it should happen actually here. At the later time. That's why we have -1 here. The other direction would be advance. So it happened before the time point 0. So the easiest way and most recommended way would be to use the same test, say nn -1 equals to 0, not equals, but bigger or equals to 0, and cast that one to double. Let's see. Oh yes. Okay, so now it starts the signal at point 1. Okay. So those were the fundamental signals. Now how about the sampling? So we have, for example, x of t equals exponential. I like exponentials. Say, let's see, 0.1 times. Oh, okay. Let's make it like that. 0.001. Let's make it minus 0.001 times t. Let's see what I have to think of it. No, sorry. Let's make it just like that. T or tau. Tau is the time constant of your RC circuit. Tau equals to RC. And now just a one small interruption. Alright, let's continue the stream. And so where are we? Okay, so we have a sampled signal, exponential signal from a RC filter, for example. You hit it with a impulse or a step function, you start getting it. So it would be high pass RC filter. And they say, okay, So we might have basically, for example, a reasonable time constant would be, say, 1 millisecond or something like that. Right. Let's mark it there. Tau equals 1 millisecond. So yes, we can use the IEEE form of the numbering. So 1 times 10 to minus 3. So that's 1 millisecond. Okay, so then we need the sampling times. We have a nice vector of sampling indexes. What we are missing is the sampling rate or sample time. And this one, to make some sense, let's put the sampling rate, for example, 2000 samples per second. So this is the sampling rate. Oops. All right, which means that we have the sample time is 1 over fs. Oops. Sample time. Ha. Good. So now we are all set for sampling, where we just replace the t with n times ts, or n divided by fs. So let's see, we'll call it xx equal to exponential of minus t is now n times ts divided by tau. And I really hope that it makes some sense. Anyways, this is what we'll get. We will see if our sampling rate was enough or was it too much in order to capture the most important part of the signal. Okay, there we are, and let's try to stem it. Oh, okay, it makes sense, kind of, sort of, but it just needs one more part, which is when the signal actually started. So it was a test signal. Your observation point is probably time 0, meaning that before the time 0 nothing happened, meaning you need to actually multiply this one with the step function. So okay, and for fun I'll just multiply that with the since I have the time delayed step function. You can do also calculations on the inside of other commands. Okay, there you go. That's the sampled exponential which starts at time 0. Good. All right. One observation. This you might already know. This is actually vector product, so that you do element by element product. Dot star means element wise product. If you multiply, I'll show you a mistake. Multiply vectors like that. MATLAB actually assumes that the vectors are properly sized, meaning that you can multiply only row vector by the same length column vector, or the other way around, or matrices that match the dimensions. The inner dimensions must match. Okay, there you go. Inner matrix dimensions must agree. That's what you get if you try to multiply two same dimension vectors. Okay. So now we have the sampling, we have the delta, we have the step function, then we have the delay, how to scale it. So half of the exercise is already covered. I need to take a quick look at the exercise. Okay, then we do some small fun part. This is for fun, but actually at the end of the day we will or actually at the end of the course you will find out this was not just for fun, but actually this is the kind of one way to test the systems. And but anyways, for now it's fun because it will make some serious noise. Noise is fun. Okay, so how to generate sound samples other than, you know, yeah, that was the sound sample. It's as close as you can get easily with the unit impulse function. As close as you can get. Okay. Okay, but anyways, sound samples. Let's sample some sinusoid signal. Wow, there's a lot of essay there. And I'll start by generating the say setting up the system here. So let's see, y of t continuous time signal, and let's put it in amplitude, for example 0.2 times sine or cosine, I don't care, 2 times pi times a physical frequency. Now I'm using a physical frequency of 1, 2, 3, and that would be my, well, actually the SSS number, 2 times pi times physical frequency times sampling time vector t. And for this one to make any sense, the time region of this one should be at least, say, seconds, or at least hundreds of milliseconds. If you put 10 milliseconds there, it's about the same time it takes sound to travel from here to that corner, and that's not very long sample. So let's see, 1 second sample, and I will start with a little bit different way as we have been sampling things. I start using the auto indexing to create a sampling time vector, but at fs equals 44,100. So that's the CD quality audio. So first define that one, sampling rate of CD quality audio. Okay, there, and then the vector t equals, so this actually is already n times t. I could also call it nt or nts. I can call it any with any sensible name. Okay, so your programming teacher probably have already told you how to name the variables, and you failed miserably on few first exercises because you didn't follow that. So all of those variables, try to make name these variables so that they make sense. So I use very short variable names because, well, I'm an old guy. Okay, you are younger, you have, you know, fresh hands, you can type longer variable names as long as they make sense. Okay, for me NTS makes perfect sense, is n times ts. All right, so but anyways, I start the time from 0. I want to go to 1 second. Okay, but I want also to sampling rate to be fs. So that's actually how you do it. So 2 colons means from, with the time step or with the step, 2. Okay, so that's the sampling time vector. The SSS would be our signal frequency. Just to make an example, so this is last 3 non-zero digits of your student ID number. Okay, so student ID number. For example, if you have a student ID number 2001506, last 3 non-zero digits are those. So your SSS equals 156. That's how I actually have scaled the exercises so that they more or less make sense. So you have all the numbers between 111 to 999, which is already 1 decade of dynamic scale, but anyways it works. So SSS comes from your own student ID number, this time 156 there, and now I can generate my sound sample. Clean sound sample without any noise. 0.2 times sine 2 times pi times SSS times NTS. Okay, so now basically I check if you follow my speak or my text there. Don't do the following. Okay. And why you should not do the following? Because there's absolutely no information on that picture. It just shows, okay, we have a mess. Okay. So what I want you to do actually is to play that sound with, let's see if the sound actually is connected. With the sampling rate. Nothing happens, so the sound is not connected on this computer. I'm not fixing it because I'm streaming, so I'm start fixing. I probably broke the stream, but someone could actually try sound of that one and to give us an example how it sounds like, if you get that far. Anyways, it should see 156 hertz sound, which is yes, that one. Thank you. But that was higher. That was close to 1 kilohertz, I think. 156 is quite low frequency. Anyways, so that's how you play the sound. Next thing is then how to put some. Let's see. Yes, signal to noise ratio. How to create their noise. I leave the signal to noise ratio calculations to you. I will just give you some hints. Okay, first of all, signal to noise ratio. That was the power of signal divided by the power of noise, 10 base logarithm times 10, or the actually 20 times log of 10 standard deviation of the signal divided by standard deviation of the noise. It was variance squared, so deviation like that one. Okay, what you need to do is now basically calculate. First of all, measure your signal, since now you have a luxury of measuring your signal variance. Although it's sinusoid, you should know it by heart or by math. But anyways, the STD of signal is simply STD and SS. Standard deviation, right? Does it make sense? It should. It's sinusoid. There's a square root of 2 somewhere. Okay, and just the amplitude was 0.2 divided by square root of 2, something like that. So the standard deviation is now, we know this one. Okay. This is set to SSS. You need to find out now the noise variance, or the noise STD. Okay, and when you get this noise STD, you actually take the random number generator, take normally distributed numbers with mean 0 and variance of 1, and multiply it with this standard deviation. And this noise now can be added to the signal, the noiseless signal. So for example, if you get a STD by doing the calculations from there, you get STD of the noise, for example, 0.5. That's the linear scale. And this is basically noise amplitude. Well, not amplitude. This is the deviation. Then you take the random numbers. No. Or no. No. Better. No, might be actually a reserved name. Okay, so then we have the that is the scaling, and then you get actually I know that it's called random. Okay, how do I know it? I have been using MATLAB since 1984. Where were you when it was 1984? Yes, I'm old. Oh no. The okay, and then it just requires the size of your vector, and you get the size of your how many points. You need to generate one random number for each point on your test vector, for example like this, same size as SS, and then scaled to the that noise amplitude there. That's how you get the noise, the correct sign of voice. You just need to do some math here. But being an engineer means that you must know the decibel scale by, even if your mother comes at the 3 a.m. waking you up, do some calculus on decibels now. You should be able to do it in 5 minutes. It's called engineering. Okay. Maybe not. But anyways, the and then, well, you can add these noises, the voice and noise together. So SS and OI is equals SS plus NOI. Okay, this should have exactly the correct amount of noise on it. Like that. Good. So what does this one look like then? Well, it does look like a noisy signal, but it's more interesting actually how it sounds like. Unfortunately, I don't have the luxury of the audio right now here. I'll fix it for the next time. But that's how you generate it, and then well, it should sound like a hissing sound. Since S actually is spectrally wide noise. Yes, thank you. There's a hissing sound is from the noise, and then there's that one, the tone, 156 hertz. So it's C. Oh yeah. It looks like a noisy signal. Yes, yes, yeah. Yeah, looks like a noisy signal. But it still has the sinusoid, and it actually shows up on spectral space. Why do I know that one? Think of your hearing. You are not hearing any single values. You are hearing in spectral space. That's why music is so nice to your ear. And you know the physiology of your ear actually, how it works. By vibration, the sensing elements actually are vibrating and giving the signals to the brains that, oh, there's some voice. So it actually works on the spectral space. Okay, next. And the final hint for today is that how to save this one so everyone can hear your nice signal. There are some commands to do it, but let's see, there might be even, let's see, export. Does it have an export? No, I don't see it here. Okay, but anyways, the you can export this one by applying wave write. Let's see, doc wave write. If nothing else works, check the documentary. Actually, this MATLAB has probably the world's best documentation ever on any of the programs, since this help actually gives you help. You can search for help, and then if you remember the name of the some function, you can check how it works. And yes, so wave write. Oh, has been removed. Audio write. Let's use the audio write instead. It even tells you that you are old and you should actually update to the newer version. So audio write. Okay, much better. The audio write, file name, data, sampling rate, then actually. Okay, I think that's just fine. So actually it can handle all sorts of file formats, but yeah, that I think the WAV files can actually be used everywhere. But okay, let's see. MPEG would be fine. You just need to set this function to actually produce the correct format. And if it was my subroutine, actually I would actually check what kind of file extension there is and then write that format. Maybe it works like that. You have time to read the documentation. But anyways, I'll just do something here. So audio write, file name would be, let's see, foobar wave. Sorry, I think I need to use a single prime. Yes, foobar.wave, data, ss noise, fs. Then the rest of the parameters would be to set up the values correctly for the saving. However, I think this would do just fine. It might actually now start complaining about clipping values, since let's see, let's go to the figure again. As you can see, this is more than from -1 to 1. And by scaling, actually, it might start losing some data. Well, what we will see. It doesn't break if I yes, data clipped when writing file. So it actually scales the data from -1 to 1. But no, yeah, the scales only the data, uses only the data from -1 to 1, and the rest of that was clipped.
So is it just a convention into that?
Yes, yes, yes. It's yeah. It's just function. Yeah. But there are also ways to rescale it or use some other format. I think MPEG can actually handle the, usually on the amplifiers have a scale from 0 to 10. So some file formats actually have 0 to 100. Okay, but anyways, it's still there. It's just a little bit clipped. We clipped some noise out, but who cares? Okay, but anyways, we have the that foo-bar.wave here, so now you can then move that to your Google Drive. So how to actually put a link to this one. Sometimes I get a link to a file that actually is on C drive. Not a good idea. So let me show you quickly, just as a reminder how to actually now put a link to this one. Earlier we put a graphics, included a graphics on our template. Okay, but here provide a link to your sound sample. So it means the sound sample should be somewhere available. Let me take a quick look. Where should I put it? Maybe I'll put it, well, maybe there on a pics, just for fun. Well, no, I want to use some of those other files. I will put it here. Okay. There I have it. Only I have access to it. So if I put a link for that one, it does not open and I would lose a point. So first things first, share it. Anyone with the link can view. There. Now I copy this one. There's the address, done. And then I can provide a link. There. That's a link that I can click. And it should open, like that, and it sounded like that without any audio. Okay, so that's how you do it. And remember, after finishing, go and publish this one so that anyone with the link can actually view it, and then test it. Test it, for example, sending a link of that one to your friend who can then access it without your Google login to test if it opens. Since every time you are missing something that I cannot open, he will lose a point. Okay, so if I calculated correctly, you should have enough of information to survive. Create index vector, use previous vector, unit step function, sample data vector with sign, and then data sequence, stem plot, those again data sequence with some delays, and well, also this kind of the box function, generate, then some sound. The hard part is to figure out the linear scale of your noise factor. The rest of this quite mechanical. Then again, the last obstacle is how to make the link to your sound file. Okay, so that's my show. I will be here until let's see, 3:45 ish to help you getting started and going through the exercise. And this exercise deadline is next week Monday at 11 o'clock. So before the next class starts. Deadline is 1 week. Okay. MATLAB is installed on all of those computers. If you are using MATLAB on your own computer, make sure that it's a legal version. Remember what I said about about being professional. Don't steal anything unless you are, of course, a theft professional. So use the legal versions. If you do not afford legal version on your own computer, then there's Octave, which works just about the same as MATLAB. It's just missing some special functions and special toolboxes. Okay, good. That's all for now. Now I'm shutting up, and then you can start working on the exercises.